You may be wondering, where do vector components come in with energy and work when they're scalars? Well, we use vectors to find the work because work can be found using a vector dot product. So let's take a look at that aspect of vectors and components and work and energy. In this problem, we're looking to find the work done by the rope that has a tension T as we pull this box across the floor with a displacement of 4 meters. And work is a dot product, the force with the displacement vector. I'm using S instead of X like I've used in the past because it doesn't have to be a one-dimensional problem. It doesn't have to move in the horizontal direction. Our object could be moving vertically or at an incline, and so S is a little more general for a displacement. Of course, if the force is constant, then this becomes a dot product with the force and the displacement vector. And that's equal to the magnitude of the force, the magnitude of the displacement vector, and the cosine of the angle you get when you put their tails together. If my force is in this direction and my displacement is in that direction, I put their tails together, that's the angle I take the cosine of. So using the dot product here, if the tension is up and to the right at an angle beta with respect to the horizontal, and the displacement vector is to the right, then my work done is equal to the tension times the magnitude of the displacement times the cosine of beta. And plugging in the numbers that were given, 346 joules. Now let's take a look at this again, but we'll use our components instead of the dot product. So if we look at our problem, we can break up this tension into a component that's in this direction. I'll call that T parallel to the direction of the displacement, and a component perpendicular to the direction of the displacement. The parallel component I know is going to be T times the cosine of beta. And the perpendicular component will be T sine beta. Now I say to myself, T perpendicular doesn't do any work, doesn't change the energy of my object. It's perpendicular to the displacement. All the work is being done by T parallel. So I could have said here the work done is equal to T parallel multiplied by the displacement. And since they're in the same direction, I know it's going to be positive work done. Let's take another example of a box on an incline. If we move our box a distance up the incline, and we want to know the work done by gravity as the box moves up the incline, well, the force of gravity points in this direction. We get a dot product with the force of gravity and the displacement. That's the magnitude of the first vector, the magnitude of the second vector, and the cosine of the angle you get when you put their tails together. Our displacement is in this direction. F sub g is in this direction. And this angle here is theta. And what angle is that? That's 90 plus beta. We could also break up the force of gravity into components. We would have a component that points in this direction, and we would have a component that points in this direction. And by the same logic we used earlier, knowing that it's a dot product and that the perpendicular component does no work, we would just use the parallel component. Now it's still a dot product. We've got our displacement going up the incline and our F sub g parallel going down the incline. And so we get an angle here of 180 degrees. The force of gravity is doing negative work on our box as our box goes up the hill. So I want you to be careful when you see an equation. We always use theta for an angle. It's just a generic symbol for an angle. Any angle we typically denote with theta. So in our formula, you have to understand this is the angle when you put the tails together, the force and the displacement. It's the angle you get. And it's not always the angle given in the problem. It's not always the angle of the incline. It's the angle you get when you put those two tails together. So as we saw with our friction, theta was equal to 90 plus the angle of the incline. With friction, it was 180 degrees. It didn't matter that the object was on an inclined plane. The force was opposite the displacement. And the work done does not depend at all on your choice of coordinate system. You could call up the incline the positive direction. You could call down the incline the positive direction. We should all get the same work done because the work done only depends on the relative orientation between the force and the displacement. And it does not depend on the coordinate system and what direction is positive.